be making an EDLC without a separator. And what we're going to be doing is that we're going to be simulating this capacitor by plotting the cell voltage as a function of time, the lithium concentration, and the electrolyte potential, and as well as the EIS. In this slide, this is just a basic gist of how our cell is going to look. We're going to have the LiPF6 electrolyte, and as well we're going to have the lithium metal electrodes. These are going to be the equations that RandFlux will be using into solving this, as well as these are our constants that we'll be using for our materials. So here we're going to be applying the EDLC without a separator, and we're going to be modeling the cell voltage, the electrolyte potential, the concentration of the electrolyte species Li plus and PF6 minus, and we're also going to be plotting the EIS. So some of the stuff that we've done before is going to be copied over here, as in what we did for the structure, making it electrolyte only, also having the initial conditions be 1000 for both the Li plus and PF6 minus. The only thing different that we're going to be doing is that we're also going to be making a double layer model for both the anode and cathode. Make sure that the affinities for the Li plus and PF6 minus are equal to 1. And another thing that we also want to make sure is that the cross-sectional area of this device is going to be 1 centimeter squared. So once that's all done, we save this, and then we create a new simulation. Move this over here, and we're going to be saving this as simulation 2. We don't really need to compute bias points, so we can get rid of this. And I'm going to create a comment so that we can a comment bar or a comment job so that we can separate the different jobs. So in this section, we're going to be doing the cell voltage, the electrolyte potential, and the concentration of the electrolyte species. So I'm just going to name this, or put under the description, cell voltage. And under the set variables, it's going to be similar to what we did in the previous video, as in what we changed. And we're going to have cathode current be negative 1e minus 3, and the resistance values, we're going to have anode resistance be equal to 0. So the next thing that we're going to be doing is that we're going to do a sweep variables, and we're going to be sweeping under time. We're going to be doing this from 0, and we're going to go all the way to 0.01. Make sure that you use a period on this one if your locale is the US version. That way you don't because if you accidentally mispress the comma instead of the period, it's going to see this as a 1 second instead of 0.01 seconds. So the next thing we also want to do is we're going to be changing this initial steps to be 1e minus 3. The minimum step to be 1e minus 4. What I said before with the initial step being 1e minus 3, not minimum step. And we're going to have the maximum step be 60. So next we're going to be doing a plot 2D, and this pane name is going to be named cell voltage. With the curve that we're going to be doing is going to be called cathode. It's going to be done over time. And the y-axis we're going to be using my device cathode potential. Same pane name as before, so it's under the same plot, except this one's going to be the anode. Same x-axis, and we're going to change this to be the anode potential. And that's what's going to be done for the cell voltage. The next thing we want to do is that we also want to plot the electrolyte potential. So we plot the electrostatic potential of the electrolyte, and the minimum makes it smaller so I can press OK. Next thing I'm going to do is we're also going to plot the concentration of the electrolyte species. So we're going to be, no, not this one. So we're going to be plotting the concentration of Li plus and PF6 minus. So lower this again so I can press OK. And then we save the simulation. And now we run it. So this here is the concentration of the electrolyte species, and as well this is the electrostatic potential of the electrolyte. And here we also have the cell voltage, and we see that the cathode voltage is going a little bit over 2 volts. So the next thing we're also going to be doing is that we're going to be, this is going to be the EIS part of it. So as to what we did before with variables, we want to create a custom variable. We're going to be naming this F for frequency. And then we're going to be resetting this. Do set variables. Go move this down a little bit. Also, we want to close this one. So we're going to set the frequency to be equal to 1e minus 3. And next we're going to be doing a small signal analysis. It's going to be the same parameters as we did before with the small signal analysis. And this is going to be the cathode potential. We're going to be naming this Z. The signal is going to be the cathode current. And this is going to be the frequency of variation, F. Next thing we also want to do is that we also want to have this F, or the frequency, increase with each iteration. So we're going to create another set of variables. And this F is going to be 1.1 times F. Next we're going to be doing a plot. This is going to be the EIS. And the curve name is going to be called impedance. So on the x-axis, we're going to be having the impedance, or in this case, resistance of the device. So we're going to have the real values for this. And on the y-axis, we're going to have the imaginary values, or in this case, the reactance. Oh wait, no, not that. Press OK. And the last thing we want to do is that we also want this to be repeating. So we're just going to have and a repeat. It's going to do the previous 3 jobs, and we're going to have it be some arbitrary large number like 1e to 5. But we're going to create a constraint so that f cannot be greater than 1e to the 4, for example. And once we do that, we run this so we can see the EIS. Oh, so in future references, to make this go faster, you can set this to be 0 so that the output file isn't showing you anything, so that the simulation is faster. So I can just show you a quick example. I'm going to do the same thing again with the EIS, and it's a lot noticeably faster in comparison to before. So the plot looks weird, but so what you want to do is you want to zoom out. So we're gonna use our mouse scroll bar and we're gonna scroll down. See how the plot changes when you look at the scale differently, and that's a straight line, and that's what you should be expecting for a capacitor when you do the EIS for it. And that concludes this video.